This lesson is about the difference quotient and rates of change. We're going to start with one of our parent functions from grade 11, f at x equals square root of x. That's the radical function. The first thing we're going to do is draw it. Then we have some other things we have to do, but let's start with that. Now remember, this is one of those functions you should be pretty familiar with. Try to visualize it. It only occupies the first quadrant when there's no transformations, right? The vertex is at 0, 0 and occupies the first quadrant. So you're going to draw your axes in so that it reflects that. So I've got my y-axis about there. I'm just putting it really close on the x, nice down low there to the side. Now we're going to draw in our function. To remember what the function is, if you don't remember what the function is like, you can sub points in your head really quickly. Use points that are perfect squares. So when I sub in a 0, the square root of 0 is 0. I have the point 0, 0. The next point I'm going to sub in for an x value is another perfect square number, which is 1. Sub in a 1, we get 1, 1. Sub in a 4, 4, 2. Oh, my points are erasing there. Sub in a 9, that would be the next one. Square root of 9 is 3, so we have 9 and 3. And the only other one we can maybe fit on here is 16 and 4. I'll put that point on. Then we're going to connect all of these red dots with a smooth curve. Like that. And an arrow there because it continues on to infinity on that side only, not on the other side. So that's the first step, is to draw the function. Now the next thing we need to do is attempt to draw a tangent line at x equals 6. So x equals 6, I'm going to put a dot there at x equals 6. It's about here. I'm putting it kind of in a light blue. That's x equals 6. Now I want to draw a tangent line there. The tangent line means I'm going to try to draw a straight line with a ruler that skims off my function and just touches at 6. So I don't want to cut through. I don't want to draw a line like this, for example. That's not a tangent line. I want to draw a line that just cuts through, doesn't cut through, but just skims across the top. So you should be drawing that blue line with a ruler. My tablet doesn't work well with rulers. It sees the ruler and it tries to use that as a pen. So anyway, draw a straight line there that just touches at 6 but doesn't touch anywhere else. So that's the tangent line. A tangent line is not a secant line. Secant line was our last lesson. It cuts through twice. A tangent line just touches at one point. So what we want to do is calculate the slope of the tangent line. This is our next step here. We want to calculate the slope of this tangent line. So how am I going to get the slope of the tangent line? Well, what am I actually going to do? I'm going to estimate the instantaneous rate of change. So instantaneous rate of change is the slope of a tangent line, not a secant line. So if I can actually calculate this, if I drew this correctly, and I can calculate its slope correctly, I will have the instantaneous rate of change. I will know exactly how my function, my red function, is changing when x is 6, if I can get the slope of this blue line exactly. We're not going to be exact today, but this is our first step in that process. First, we're going to use a value of x just to the right of 6. So we're just going to move a little bit over 0.01 units beside x. So we're going to be looking at 6.01 right over here. We want to look at a point on the curve, on the red curve, that's just beside 6. And then we're going to do that, and we're going to go even closer. We're going to go 0.001 units to the right of 6. We're going to get even closer to 6. We call these very small values h. So first we're going to use h equals 0.01, and we're going to find the slope between 6 and 6.01 on the red curve. Then we're going to use 0.01. This is called a squeezing method because you're getting in closer each time to your value that you're investigating. So squeezing interval, calculate the rate of change over a very short or tight interval with the left end at x equals 6. So x equals 6 is right here on the left. We're going to go just to the right of it, just a tiny fraction to the right of it. And we'll do it twice. We'll calculate it using this interval, and we'll calculate the rate of change using this interval, and then we'll average our two answers together. So here is our basic formula. Now I've got I in the front there, instantaneous rate of change. Instantaneous rate of change, so it's the same form as yesterday, change in y or change in x. So this is another way of writing y, f at x. So we sub in here. So I'm looking for how my y values change. So I want to know my function value at 6.01 and my function value at 6. And then the difference in that will be 0.01. The x2 minus x1 would be 0.01. So we're going to go back up to the function in the question and we're going to sub in here. F at 6.01 means I'm going to go up to my function and I'm going to sub in a 6.01 there. And then subtract back up to my function again and sub in a 6. And then my denominator, I already know what that is, it's 0.01. So you get out your calculators and we're going to be rounding here, estimating. So this is approximate rate of change here is about 0. Well, there's a lot of numbers here, 2040, and it continues on like that. We're going to do this twice, so let's just start with those numbers there. So that's the first part. The question asked us to do it twice, the squeezing interval. So we just found the slope between 6 and 6.01. Let me try to highlight that here on the graph. Here's 6. 6 is the number that we are looking for the slope, right here at 6. So the way we did that was we found the slope between 6 and just to the right of it on the red graph. So we actually did find a secant line because we're still on the red graph. We're using 2 points on the red graph and we're finding the slope between them, but those 2 points are really, really close together. And the slope is a really small number, as you can see, very small, because the slope between these two, because of the shape of this curve, it's getting to be pretty flat, right? So it's a pretty small, a pretty low number. It's not a very steep curve. So we're going to do all this again, but this time we're going to get even closer to 6 on the red curve. So we're going to use the same formula. Let me switch colors. We use the same formula here, but we're going to do it all again. So we're going to find the instantaneous rate of change again. Approximately instantaneous rate of change. So we're going to this time find out where our function is 6.001 and we'll subtract f at 6 and then our denominator will be 0.001. So subbing in to our function, that just means we're looking for the square root of 6.001. Subtract the square root of 6 all over 0.001. And that gives us a very similar number to what we had in red there. 0.204, and then I've got a 1 after that and some other numbers. So those two numbers are really close, and they should be really close because they're really looking at the slope of the red curve at almost exactly the same spot. So we've got the instantaneous rate of change for both of them. And then we can add them, we're going to add them together, average them and divide them by 2. But since we have just another method here, since we have the same decimal values, we're kind of confirming one answer with the other because they're so similar. We can just kind of summarize and say, therefore, the instantaneous rate of change of this function at x equals 6. So what this is saying is, what is the slope of the function just at that point? It's about 0.204. Now we don't have to put any units on this. This isn't a word problem, so there's no degrees or seconds or anything like that. It's just a number. So the next slide here, I'm just going to review a bit. This was our last lesson. This was the slope formula. We just changed y2 and y1 here. Remember that an average rate of change can be used, it's an approximate, because you're looking for a secant line. You're taking 2 points on a curve and you're connecting them and you're finding that slope. Right now, we're just going to take x1 in this equation right here, and we're going to change it, just another different notation change. We're going to call it a, and you'll see this a little better in the next example. These little h numbers that I already introduced you to, h is a very small number. When you use this formula now, which we're going to substitute in an h, it's called the difference quotient. So it's still a rate of change, but we're using this formula now. And if you think of the example we just did, that's what we had on the denominator, right? Our x2 minus x1, we had 6.01 subtract 6. We just end up with that really small number there. So we just go ahead and substitute that really small number there. And then a is the number in question. In last case, it would have been 6. And then this is just a little bit higher than 6 there. H can't be 0, of course, because we can't have a denominator of 0. So that's why we're always subbing in these really small numbers. It's still a secant line because technically we're still on that original curve. We have 2 points on a curve and we're finding the line, the slope of the line that connects them. So that is still a secant line. So it's not a perfect instantaneous rate of change. We will get there later in this chapter, but right now we're getting closer. Example 2. So we've got a cubic function here. We want to estimate the instantaneous rate of change when x is 1.5. We're going to use the difference quotient method. That's the new one I'm showing you today. You can perform the calculations twice, so this isn't new. Once with h equals 0.01, but then this time we're going to use a centered method that we learned in our last lesson here. So we're going to go to the other side of 1.5. We're going to go just to the right of 1.5. We're going to go just to the left of 1.5. Make sure you start by writing out the formula first. So here is the difference quotient. This formula you have to memorize is the difference quotient formula. So it's a little bit different from, it's still a slope formula. We're just changing our variables a little bit because we have an a here for this value. A is the x value you're investigating. In this case, this is our x value here. So sometimes students they'll leave it an x here, and that's fine. I often do that too. I put f at x plus h and f at x, and then I just use this x value here. So you can leave it an x or an a, but you'll just be familiar with seeing both of them. So we are going to start on the right side of 1.5. We're just going to go a little bit to the right of 1.5. So subbing into the formula, there's my 1.5, that's my a value. My h is 0.01, and there's minus f at 1.5. So just to tidy that first section up a little bit, that's saying f at, so I'm going to add those two numbers there, 1.51 minus f at 1.5 all over 0.01. So now we have to calculate f at 1.51. So you're going to take 1.51, you're going to sub it in here, 1.51, cube it, subtract 2. Once you do that, you'll sub that in here. Do it again for 1.5, sub that in here. So you can press pause and go ahead and use your calculator and get those numbers and come back and look at the next line. So I've got an instantaneous rate of change that is an average, approximately 6.7951. So that is what the function is looking like. So let's just make sure we understand what we're talking about here. If I drew this function, let me just do a quick sketch here. If I were to draw the function, we're talking about x cubed minus 2, something like this. Shouldn't be curving back, something like that. And then what I'm looking for is I'm looking when x is 1.5, right? So wherever x is 1.5 on here, let's say it's there, maybe that's 1.5. I want to figure out where is my graph? What is the slope of my red curve there? So just using 1.5 and just beside 1.5, I get the slope to be 6.7951. So let's try it again, but we're going to go on the other side. We're going to use h equals negative 0.01, so we're going to go on the other side. Now, it's really important that you always start with a formula because you have to put these values in the right spot. And if we're on the left-hand side of our number that we're investigating, in this case it's 1.5, you might get your numbers turned around. So let's make sure we put them in the right spot here. 1.5 is our A. This time our H is a negative 0.01. So we're going to go ahead and let me just simplify that a little bit. That's the same as F at 1.49 subtract F at 1.5, oops, 1.5 all over negative 0.01. So to get your values here, you're going to go back up to our function and you're going to sub in for x, first 1.49, sub in for x, cube it, subtract 2, get all that. Then you do it again for 1.5. So you can press pause here and finish that, and then you'll see the answer when you come back. So we've got our answer here, and our two answers validate each other because they're very close to each other. 6.7, right? 6.9, 6.8, they're very close. So we know that our slopes are really close to each other. And then the next thing we're just going to do is add them up and divide by 2 and get an average. So the average of these, therefore, the average of these gives us an IROC of approximately 6.75 when x equals 1.5. So here we have a little word problem, but this is different than what we've done. We have an equation, and it's talking about profit or loss. It's a cubic equation, and we're looking to find out, it's telling us that there's a critical or a turning point. So it's like a parabola would be a vertex. It's got a critical turning point at 2, -2. But how do we know if it's a local max or a min without graphing? Now, we'll talk about the word local later, but is it a max or a min without graphing? So what I mean by that is, let me just draw say, here's a cubic. Here's a cubic. This is not the right answer. I'm just drawing a little sketch here. Here's a cubic. So let's say 2, -2 is, put some axes on here. Let's say this is my, no, let's put that a little higher. 2, -2, go like this. And maybe my y-axis is here. So if this were 2, -2 right here, this point right here, there's my 2, -2. 2, -2. Is it a max or is it a min? Now I've drawn it to look like a minimum, but maybe it's not. Maybe the 2, -2 is the other one, because I just threw in the axes myself, right? So how could I determine if that is a maximum or a minimum? Let me draw it the other way. If I had a graph like this, but my axes are here and here. Maybe that's my 2, -2 there. I don't know exactly. So how do we find out if it's a maximum or a minimum? The question's telling us it's a turning point, but how do we know? We can calculate, erase some of that. We can calculate this. So we're going to look at the time value in months that we're investigating is t equals 2 months. That's the x value here. That's what we're looking at. If we calculate the slope just to the right of t equals 2 and then just to the left of t equals 2, we can find out if it's a maximum or a minimum. This is unlike our previous examples. In our previous example, the one we just had, we had an x equals 1.5. We went just to the right of 1.5 and we went just to the left of 1.5, and our answers were really similar. They were both 6.7. They were very similar to each other. That won't happen if it's a turning point. Your slopes will be different. So what we need to do, let me just put my sketch on here without a grid. What we're trying to do is, if it's a minimum, if this is my 2, -2 here, I want to calculate the slope just to the right of it. So let's say between these two red points, I calculate the slope just between these two red points here. This slope would be positive. That would be a positive slope. Then I would, let me switch colors, I would go just to the left of my x value of 2, just to the left of it here, calculate the slope between these two, and that slope, if it turns out to be negative, that would tell me that I have a minimum. that would tell me that the question says that it is a turning point. So if I get the slope to the right and it's positive, the slope to the left and it's negative, then I know I have a minimum. What about if it's not that point, but if we're up here, I'm going to go to this the maximum. So let's say that is my t value of 2 right there. That's t equals 2. So I go just to the right of that, say 2.01, right here, this purple dot, 2.01. Then I find the slope between those two, and that, the way I've drawn it there, that's a negative. It doesn't matter what it is. It could be a big number or a small number, but it's negative. I only care about the sign here. Then I go to the other side of it, just to the left, let's say 1.9, just to the left, I calculate the slope between 1.9 and 2, and I get a positive. That would tell me that my turning point is a maximum. So press pause here and make some notes for yourself on that. Try to summarize what I just wrote there. So I will tell you the answer for this one. If you calculated the slope just to the left side, if you actually did the math here and you calculated the slope on the left side, so let me highlight that here. First I'm going to go to the left side on the left side here. Here's the left side. If I do the left side, or that's the left side there, I've highlighted both of the left sides. If you I've found the slope on the left side, I calculated that, used the formula, and I found that to be negative. Then I'll highlight again, I went and calculated the slope on the right side. So on the right side, so I calculated the slope on the right side, and it was positive. So does that mean it's a max or a min? So therefore that means -2 is a minimum, because when I calculated the slope on the left side of the function, I got a negative. On the right side, I got a positive. So it must mean that I have a minimum there. Negative, positive. Doesn't matter what the numbers are. They're pretty close to each other. Like this might be a -0.5 and this might be a positive 0.5. So the values the absolute values are similar. But one is negative and one is positive because it's a turning point. So that tells me it's a minimum. So this question was just how could we determine it? So we didn't actually have to, but that's what we would do. So this leads very directly into our next topic. That's why I do these two together. We're going to draw a diagram illustrating you've heard me already saying local max and min. So now I'm just going to show you what that means. So let's draw kind of a weird shape here. I'm going to start with a dot up here, and then I'm going to draw some curves and twists. You come down like this, and then up, and then down again, up, and let's just go like that. Okay. Local max is the first thing on my bullet list. Local max. So we've got local max and absolute max. The difference is absolute max means absolutely the very highest value that your curve or your function has, and that would be right here. This is the highest it gets to. It comes up and down here, but it never gets higher than that. So that point right there is my absolute. It's the absolute maximum of the graph. This is the absolute maximum. Absolute max right here. If hopefully you drew it the same way I did, and that is actually your absolute maximum. So that's the absolute maximum. Now, the next one we're going to look at is a local maximum. Local maximum is also a maximum, but it's not the biggest one. So this point right here and this point right here, these two are local maximums. And that's what we had on our cubic before. We had local maximums. Here and here, local maximums. The next one we're going to talk about is the, we'll do the absolute minimum first. Absolute minimum would be the very lowest the curve gets to. Because of the arrow on the bottom here, this graph has no absolute minimum because it goes to infinity. No absolute minimum. What about local minimums? Yeah, we've got local minimums. Well, we've got 1, 2 right here. Here's a local minimum, and here's a local minimum where I took my 2 light blue dots. Those are both minimums. They're not the lowest the graph gets to. It gets much lower than that, but we call them a local minimum. So there's a local minimum, and there's a local minimum. Now we want to add onto our diagram. Now we want to talk about rates of change. So the first one says a positive rate of change. A positive rate of change, remember Mr. Slope Guy. Mr. Slope Guy looks like this. So positive slope goes up. A negative slope comes down. A undefined slope is vertical, that's undefined. And a horizontal slope has slope of 0. So this is Mr. Slope Guy right here. You've seen him before. There's Mr. Slope Guy. Positive rate of change. So we're looking right now for where we're looking for something like this. We're looking for positive, where our graph is going up. So this is coming down, but from this local minimum to this part here, this right here is a positive rate of change. We're getting, our function is going up. So there's a positive rate of change there. So what I will do is highlight these in yellow, the positive rate of change in yellow. So here's a positive rate of change there. So I'm doing these in yellow, positive rate of change. And there's another positive rate of change section right here. This is a positive rate of change. So there's 2 positive rates of change. So the next one we're going to talk about is a positive rate of change. Negative rate of change. Here's the negative indicator there. Negative rate of change is when your line is coming down, from left to right coming down. So let's highlight those sections in green here. I'll use, green. So negative rate of change. Negative rate of change, that's from where we started, coming down. This is all negative rate of change. We have another section kind of in the middle that's a negative rate of change, and all the way down, the remaining down to infinity, that's all negative rate of change, all those green parts. And a rate of change of 0, I think I'll just put that in pen here. A rate of change of 0, blue. A rate of change of 0 is when we have, so look at Mr. Slope Guy, rate of change of 0 means a slope of 0, that is right here. This is the slope of 0. It's a horizontal flat line, those are slopes of 0. So the only place I would have a slope of 0 is right at the turning point. So if I drew a tangent line right here, that would have a slope of 0. So at any of my turning points, I have a slope of 0. Okay, now it doesn't include the endpoint or absolute max. So these all have a rate of change of 0. All the turning points have a rate of change of 0. The only other piece that I want to point out is the sine wave or cosine wave. So if we have a sinusoidal wave, it has, so if this were the parent function, that's not a good drawing of it. If this were the parent function, and let's say that's a 1 and a -1, it has a lot of absolute maxes. So these are all absolute maximums here. They're not local, they're absolute because they're as high as the function gets, but it's repeated. So the sine wave would have absolute maxes, not local. Local means there's something higher or lower than it, but this one doesn't. If you've forgotten about turning points for the parent functions, just be sure to go back and review section 1.4. All right, we've got two more. Example 6. We're going to move on to a sinusoidal here. We've got f at x equals 2 sine 2x. Amplitude is 2, k value is 2. This is a point. 45, 2 is a point on the function. We're going to use the difference quotient to determine if the slope of the tangent at that point is 0. So remember what we just talked about? We want to see if this is a turning point. This is actually what the question is asking. Is 45, 2 a turning point? If it's a turning point, its slope would be 0. How do we do that? So let's start off with the difference quotient, with the formula for the difference quotient. And we have a value of 45. We're using h equals 0.01. The question didn't tell us specifically what to do, so I picked 0.01, but did say the difference quotient, so I have to use this formula. So, of course, this is my x value that's under investigation here. This is my independent value of a 45, so a 45 goes in here for a, and then 0.01. So when you start putting this in your calculator, it's important that you don't round, because we're looking for a slope of 0. And if you start rounding, and you shouldn't be rounding, your calculator, you might just round your way into a 0 when it's not actually a turning point. So try not to round. Try to write down as many decimals as you can, or you figure out how to use the memory button on your calculator. I use mine all the time, or maybe on your calculator it's STO for store, or it's an M plus or something like that. But every time I do a big calculation, I store that in the memory, then I go on and I do my other calculation, and then I can recall that out of the memory and add it to my first number or whatever it is I need to do. So come up with a number here, calculate all these values, and then come back and write it down. So I'm going to put, I'm storing numbers in my calculator here, so I'm not going to write everything down. I'll just write down a few of what I've got here. My calculator is showing me 1.999999878. I'll just put for now 1.999, although I'm storing it all in my calculator, so I've got this number here. I'm not going to round that to a 2, because f at 45 is 2, right? We had that, you could have calculated, but they told us that in the question. They told us that the coordinate was 45, 2, so I didn't even have to calculate that one. Over 0.01. So we are just to the right of 45 degrees. So if my sine wave is like this, and I'm looking for 45 degrees, maybe 45 degrees is right. Let's just put a line through like this. Let's say that's 45 degrees right there. I just went just to the right of 45 degrees, just to the right of 45 degrees. And I found, so look at, it's important that you didn't round here, because look at your answer here. You're going to get, your calculator is going to give you maybe a difficult number for you to understand or write down, but what really matters is it positive or negative? So what's important is that it's negative. So let me erase this line here. So wherever my 45 degrees is, I know that just to the right of it, I'm getting a negative slope. Just to the right of it is negative. So remember the negative slope. This is a positive slope. This is a negative slope. So wherever my 45 degrees is, just to the right of it is negative. So that could be, my 45 could be here, and just to the right of this is negative. The 45 could be here, just to the right of it is negative. So it's looking like maybe this is going to be a turning point, because we have a number that is so close to 0, but it's negative. What we have to do now is go to the other side to validate this. We haven't proven that it's a turning point. All we've proven is that it's a really small number close to 0. Right? This is really, really small number here that we got. So it's almost 0, but it's negative. So that's not really good enough. That just means it's almost flat. But I need to go to the other side of my turning point and see if I can get a positive. That would be very helpful there. So this is as close as we can get to 0 because we had to find the slope between 45 and a number right beside 45. So that's pretty close to validating that it is a turning point. But we'll know for sure when we finish part B. Part B is asking us, is it a max or a min? So we're just going to finish this off here. We already looked to the right side of 45 degrees. We did 45.01 here. So now we're going to look to the left side, and I'm going to kind of put in a different strategy here. We're going to go all the way to 44 degrees. We're not going to try subtracting 0.01 and using the difference quotient. I just wanted to review one of the methods from our last lesson here. So we're going back to this slope formula, f at x2 minus, so this is y2 minus y1. We're going to sub in everything here and see what we get for an answer. Remember from our last lesson, this is our x1. I'm labeling them on red here, and this is our x2, right? So the first one is x1, the second one's x2, so we're putting a 45 here, minus f at 44 over 45 minus 44. So our function at 45, they already told us that in the question. I'm going to circle it at the very top here. We already know the y value is a 2, so I can go ahead and put a 2 there. Function at 44, I'm going to have to figure that out, and my denominator will just be a 1. So I'm just going to write 1.998, a bunch of stuff here, so let's store it in the memory. Don't round it, because then if you rounded it, you'll get a 2, and you'd get 2 minus 2, and then that's not good. We don't want everything to turn into 0. We do need to see if it's positive or negative and how close to 0 it is. So when you finish the question, you will find that you get, let's say it's approximately 0. Depends on how much we all rounded here, 0.0012, something like that. But the point is that it's positive. It's very small, like our last one, but this time it's positive. So now we know when we are just on the left, when we're on the left side of our function, we've got, so we are looking at 44, which is just to the left. So on the left side of 45, we've got a small positive value here. So that means the positive one, it's coming up. I just put that in green on my little sketch graph here. On the left side, so this is 45, right? On the left side of that, we found we got a positive value. We found we got a positive value on the left side of 45. Wherever 45 is, it doesn't matter. So we have used question B, said use an algebraic strategy to verify that the point given is a max or a min. Which one is it? So we have verified that it is a maximum. Therefore, 45 degrees and 2 is a maximum. And we kind of did part A and B together. They're really the same question. One of them is asking you to prove that it's a turning point, and the other part's asking you, is it a maximum or a minimum? So we kind of did both at once there. We proved them both. Last example. So here's our last example. We're looking for the maximum and minimum values of an exponential. We haven't done exponentials for a while, so I'm just going to review with you a little bit about exponentials. The parent function exponential is 2 to the power of x. 2 to the power of x looks like this. It's always going up, right? 2 to the power of x. But our base is a 0.6. It's not a 2. When you have a base that is less than 1, and of course it's positive, so it's between 0 and 1, it's going to be a decreasing function. It's always going to be going down, decreasing. So it's, instead of increasing, it's always going to be coming down like this, decreasing function, always decreasing. So it's going to be kind of like that. So you would think, well, there are no maxes and mins on that. Look at the arrows on either side, right? How can we have a maximum and a minimum when it clearly continues on to infinity in both directions, the end behavior? But we have a restricted domain, so we only want a piece of this graph. We just want to look at a little chunk of this graph between 0 and 10. So think back to when we did piecewise functions. When we did piecewise, the endpoints were really important. So that's the same principle here. We want to look at the ends. I want to know f at 0 and f at 10. I need to know those values. So f at 0, let's sub a 0 into the equation. It's 55 times 0.6 to the power of 0. And anything to the power of 0 is 1, so we get a 55. So we have the coordinate 0, 55. Our other end of the domain is f at 10. F at 10, sub into 10, 0.6 to the power of 10, put it all in your calculator, and you get 0.33256. I'll just make that a 26. So let's do a little sketch here to make sure we know what we're talking about. Y-axis, x-axis. Please use a ruler when you do this. Well, if the question doesn't ask you to draw it, it's just a sketch to help you. You don't have to worry about using a ruler. I'm going to put a 10 there because that's all we care about for this graph. We've got a value of 0.55. That's way up here on the y-axis at 55. That's a value of 55 right there. And then we've got 10 and 0.3. That's pretty low. So we know it's a decreasing function, and that makes sense with my picture here. I'm just going to draw a decreasing function like that. But the only part that I care about is let me highlight this piece here. The only part that we care about is between 0 and 10. So this is the only part that I'm highlighting of the graph that matters. So now we can actually talk about a maximum and a minimum, because for that small segment of the exponential, there is a maximum value. The maximum value is right here at 0.55. 55 is the highest it gets to. The lowest, I didn't write the coordinate here, this is 10, 0.3326. This is a minimum. This is the lowest our graph gets to. So the question said find the maximum and minimum. That's all we had to do. We didn't have to do what's down here. It says this little note at the bottom. NB means pay attention, okay? Nota bene. You cannot verify whether or not these points you find are maxes or mins with the difference quotient. So these values we got, we couldn't put them into the difference quotient, and that's because the graph's always decreasing. That means the instantaneous rate of change for any point will always be negative. You're never going to get like the question we just did, where we had positive on one side, negative on the other side. We could tell from the slopes that it was a turning point. That's never going to happen here. So the difference quotient isn't helping us in a question like this one where it's always decreasing. The last thing we have to do is state the range for the given domain. Okay, the range is always set up like this. So our range is y is an element of real numbers, or I'm going to put f at x is an element of real numbers, such that, so we always put our low number here. It always looks like this. This is the format we use. High number here. So our low number, the lowest we get to was a 0.3. The highest we get to is a 55. So the range of the function is simply between 0.3 and 55, because that's the only segment of the function we were looking at. And that is the end of your lesson for today.